Hi, everybody. This is Mr. Folly, and welcome to me not being able to write to Lecture 2 on heat. This is a calculator section, so get out that calculator and let's get ready to rumble. Here's a riddle. I knew the answer before and I forgot it. Before I'm born, I was a liquid. When I'm alive, I am a solid. When I die, I'm a gas. I can die of hypothermia really easily. What am I? I don't know what that is, so maybe that'll be the pod quiz question. That wouldn't be fair because I didn't give the answer, but you get the idea. All right, heat calculation. So we know that we have to figure out how much energy it takes to do something. So when we're doing that, that means that we need to know a number of things. So first of all, for heat calculations, to make it easier, heating curves are guides to calculations. If the line increases, temperature is changing, and I'm going to put right on there MC delta T. If the line is flat, the phase is changing. I'm going to write delta H, M delta H for that. These can be combined. So, for example, if I go from A to B, hey, Mc delta T, B to C, M delta H, and I just plus those two together. Okay. If I had solid butter, I melted and put on a doorknob as an April Fool's Day joke. What part of the graph would be shown? All I'm doing is melting it. Because solid butter, I melted, right? So this is just the melting, okay? Warming something up. How much energy does it take to heat it up? How much energy? That's Q. How much of it do you have? That's M. So the heat is the mass. What determines the heatability, like in our thermos? That's called specific heat. Okay. So specific heat, symbol is C, it's calories per gram degree Celsius. A large C is an insulator, a small c is a conductor. So insulation doesn't change temperature very well, but metals do. So for example, if you're outside in the wintertime now and you put your hand on a metal, it will feel very cold because it's 25 degrees outside and touch the metal, it's 25 degrees, conducts that heat or conducts the heat from you to it, makes you feel cold quickly. But if you put your hand on like grass, the grass has a higher specific heat and it doesn't go as much. How hot do you want to make it? That's the change in temperature, right? So that's how we get the equation Q equals MC delta T. Examples, let's take a look. What will be the final temperature? Oh, okay, delta T. The other thing is delta T breaks out and equals T sub F minus T sub I. F is final, I is initial. What will be the final temperature if 20 grams of solid copper at 5 absorbs 200 calories of heat? So Q equals MC delta T. So I'm going to absorb 200 calories of heat. I have 20 grams, and I need to find the specific heat of copper. I think I have a table of all kinds of goodness on here that I gave to you. I do. So I'm going to look for the specific heat of solid copper. So notice how this is just back here a little bit. These are my specific heats. Specific heat of copper is 0.1. All right, I should have that on my side because I don't want to keep scrolling back and forth. 0.1. And then there's two ways to do this. I can do this with T sub F minus 5, or I can solve for delta T and then add that to 5. I'm going to do it this way. So 200 equals 2, multiply those two together, T sub F minus 5. Now I'm going to do the thing we do badly, which is remembering to distribute. 200 equals 2 T sub F minus 10. 2 times 5 is 10. So I'm going to kick my 10 to the other side. So 210 equals 2 T sub F. T sub F equals 210 divided by 2. 105 degrees Celsius. Okay. And all I did, if I'm looking at this, is travel along the change in temperature line. Again, solid, liquid, gas. What will be the final temperature if 20 grams of solid copper at 10 releases 200 degrees of heat? Okay, so it's solid. It's not going to go down anymore. Okay, so I'm going to have, again, I'll change my color because that's fun. I hope Q equals MC delta T. So I'm going to have 200 calories this time. Oh, by the way, do you notice how I found out this part right here? the change in temperature will be the same, right? So if I went from 5 to 105, that means that delta T equals 100 degrees. But if I release 200 calories of heat, that means I'll get colder. So that means I'll just go down 100 degrees, right? So my answer is going to be negative 90 if I'm crafty. But let's see what happens here. So if I'm releasing the heat, that means my Q is negative 200. My mass is 20. Did I have the same mass? I did. My specific heat is still 0.1, still solid copper. T sub F is what I'm looking for, minus 10. All right, so here we go. So negative 200 equals 2. I'm going to combine some stuff. T sub F minus 20. So I put some things in there a little bit differently, okay? So I did combine some steps. I'm going to kick my plus 20 to the other side. Negative 180 equals 2T sub F. Divide both sides by 2. T sub F equals negative 90. Hey, it works. Both ways works. What mass of mercury can be heated 15 degrees Celsius when 175 calories of heat are added? Now, I did not tell you what state of matter mercury is because I'm a bad person. Let's say it's liquid before we get too far. Okay? So Q equals, I got to continue my color extravaganza here. So Q equals MC delta T. 175 is my heat. Mass is what I'm solving for. I need my specific heat of liquid mercury. And it's heated 15 degrees, so delta T is 15. And let's find the specific heat of liquid mercury. I call this the table of everything. So if I say I have to look at the table of everything, 0.034. So then my mass equals, I'm going to divide by this and divide by that. 175 divided by 0.034 divided by 15 is 343 grams of mercury. Oops. Let's let that settle in. Okay, so what do we do here? We drop in our equation, we know what these are, and run with that. When we tested our thermos, 1,000 grams of water at 20 degrees Celsius was heated to 100 degrees Celsius. How much heat did that take? So again, we're going to look at MC. Whoops, let me put a Q in there. Q equals MC delta T. How much heat did that take? That's Q. I got 1,000 grams of water. I hope you'll believe me, I do know water specific heat is 4.18. No, it's not. We're doing calories. Is 1.00. And the change in temperature was 80. Hey, I can even do that in my head. 80,000 calories. Okay, so phase changes. Q equals M delta H is going to be something. Delta H is the energy change the state of matter in calories per gram. Delta H fusion is energy to melt or freeze. So fusion means stuck solid. Okay, so stuck solid. So fusion, if you fused your finger to your head with super glue, it would be stuck solid. Your finger would be solidly stuck to the fuse. Vape, delta H vape has a gas. Vape. Vapor is a gas. So if I'm going from a liquid to a gas, a vapor, or a gas vapor to a liquid, it's going to be delta H vap. M is mass in grams. Q is heat in calories. Let's do a couple. Breathing in 2 grams of benzene will cause brain damage to your dog. How many grams of liquid benzene will boil at 80 if 150 grams of energy are added? Will you give your dog brain damage? Okay, so notice we're just boiling it. I assume 80 is the boiling point of benzene. So we're going to look for the boiling point of benzene, and we're going to look for the heat of vaporization of benzene. Heat of vaporization of benzene is 94, and boiling point is 80, just like we said. Uh-oh, that made some weird shapes. Wish I could turn that off. All right, so 94, and it is at 80. So, whoops, back to this. Q equals M delta H VAP. It was 94 degrees. Now notice, because it was at 80, that's this part right here, I don't have to do any of this. I don't have to do any of that. Because you're starting at 80, you're just boiling it. Okay. I added 150. That's going to be 94. Is the, whoops, I did that wrong. 94 is the molar mass. And we're breathing in 2 grams of benzene. Uh-oh, I don't have any variables. Breathing in 2 grams of benzene will cause brain damage to your dog. So let's figure out how many grams this will make. Okay. So M is going to equal 150 divided by 94. That's going to make 1.6 grams form. That's not enough to give brain damage to your dog. No. Okay, your ice cream cake has a heat of fusion of 1.16 calories per gram. If the room provides 500 calories to a cake, how many grams of your 2,500 gram cake will melt? And we're going to assume we are at freezing point for the cake already. Okay, so we're going to do, again, Q equals M delta H. No, let's go green for a while. Q equals M delta H fuzz. Okay. The room provides 500 calories to your cake. I see this mass of 2,500 grams, but not all of it's going to melt, just some of it. So we're going to figure out how many grams of it will melt. And the heat of fusion is 500. That's not the heat of fusion, silly. The heat of fusion is 1.16 calories per gram. I kind of hate this making circles out of that, but 500 divided by 1.16 is 431. Mass equals 431 grams. No. All right, combo calculations. How much energy does it take to convert 5 grams of carbon tetrachloride at minus 30 to a gas at 85? Okay, so this is step by step what we do. So the first thing we do is draw an axis. Hey, I drew an axis. The next thing you're going to do is add the boiling point 3/4 the way up. Boiling point of, let me do this again. Convert 5 grams of carbon tetrachloride at minus 30 to a gas at 85. So add the boiling point 3/4 the way up and the melting point 1/4 the way up. So, and these are approximations, so it doesn't really matter. Label your start and end points. So we're starting at, I put it in here. We're starting at minus 30, which is lower, and we're ending at 85. Draw a slanted line up until you reach melting point or boiling point. Make it horizontal. Slanted line up, 77, horizontal. There you go. All right. Each line segment is part of the equation added together. Slanted parts change the temperature, so each slant is MC delta T. C will change. Plateaus change the state of matter, right? So PE is M delta H for each one. Now do the math, okay? So what we would do here is, if I label this A, B, C, D, E, I would say Q equals, and I would never want you to write this part down. Adding all those together, could I make it any harder to read? I don't think so. And then Q is A. A is the slanted part. MC delta T. Plus B. M delta H fusion. Plus C. MC delta T. I'm going to put a little liquid on there. This is solid. This is liquid. MC delta T. Plus M delta H VAP. Plus MC delta T. Uh-oh. I get the idea. You heard me. So there you go. All right, and then we plug it in. All right, so now, specific heat concepts. Low specific heat changes heat easily, also quickly. Low specific heat is called a conductor because it changes heat quickly and easily. Given equal amounts of energy, a low C will change temperature more than a high C. So metals change temperature more. We use that. Are greater than grass. The delta T is greater. But C, oh man, why'd you do that? I was right at my dramatic moment, and then Word hates me. Come on, Word. And delta T is greater than grass. But for C, the C of metal, wow, C of metal is less than C of grass. Okay, so there's a setting I got to change somewhere. All right, high specific heat takes more energy to change temperature. We just kind of talked about that. Preheat an oven to 450. Check, check. Touch the air. Now the air is 450, right? You go, oh, that's kind of hot. Touch the metal. Ah! Which has a lower C. Which one? Metal. Why? It changes temperature faster. Really, it's with less energy? Oops. Changes faster. Metals have low C's. Water has high C. Yes, one is high. And living things have a high C because they have so much water in them. Heat of vaporization, heat of fusion concept. Vaporization is always larger than fusion by a lot. Changing the energy change is changed. From solid to liquid is noticeable for energy. The distance increases some. You are breaking bonds, but reforming some. So the energy change is meh. Now that means it's small, but it's noticeable. Change from liquid to gas is enormous. The distance increases a ton. I'm now dividing by a huge radius squared. You are breaking bonds, but not really forming any. And then here's the table of everything I talked so happily about. And that's all we've got today. Toodles.